Okay, it's a great pleasure to have Pengfei Zhang as our speaker today. Pengfei is currently an assistant professor at Fudan University, maybe associate. Uh,
Um, that's complicated. I don't know how to
oh,
call it.
okay. Yeah, but in short, as a young scientist, Pengfei has already done a lot of interesting work across many areas, starting from AMO physics to non-equilibrium quantum dynamics, quantum chaos, to machine learning in physics. And I particularly appreciate his work on the physics of scattering. I think this series work is very elegant and uh, it's very impressive to see we can still get so many exact results. This is also the talk today. Hopefully, please go ahead.
Thank you. I'm very happy to have the opportunity to share our recent works on the Efimov effect. Actually, as Liu Jun said, it's a kind of old topic, but we can still make some progress. So today I will introduce two of our recent works. One is to obtain some new exact renormalization relation for the Efimov effect. The second work is mainly on finding a new realization on the quantum platforms. So to begin with, let me first thank my collaborators. So this talk will mainly focus on two of our recent works. One with Langxuan Chen. He is now a graduate student at Stanford, and another work with Ning Sun and Lei Feng. So Ning is now a postdoc at Fudan University, and Lei Feng is a professor at Fudan University working on the trap-down experiment. However, he also had a very broad interest in the theoretical AMO physics. So here is the outline of the talk. I will firstly give a very brief introduction to this old topic, the Efimov effect, and then I will explain how we obtain some new result for this old problem, and finally explain how we can realize the Efimov effect in a new trapped-ion experimental system. So in particular, in some long-range quantum spin chains. So to begin with, so as a physicist, we are interested in some universal properties of a quantum system. So which means the system with distinct macroscopic details can share the same emergent phenomena. So one celebrated example is a phase transition. So like when we have some quantum phase transition, we can study the critical theory. The critical theory only depends on some few parameters like dimensionality, the statistics of low energy excitations, and so on. Another universal phenomena is hydrodynamics, like the water in my cup, and also the Bose-Einstein condensate in optical traps. They are all captured by the very simple rule of hydrodynamics. So this is also very universal. And another example, so actually the main example I will focus on in this talk is the low energy scattering problem. So what is a low energy scattering problem? So let's consider this Hamiltonian. So actually, this is just a textbook Hamiltonian in the undergraduate courses of quantum mechanics. So we have a kinetic term, which is p squared over 2, and we have a potential, actually it's an interaction between different atoms. So this interaction term is assumed to be short range. So actually in realistic systems, all the interactions can have some long range tail, but I will not discuss in details. But just trust me, there are some systems where this power law tail of the interaction is not important. So for example, in the AMO physics, so atom interact with a van der Waals potential. So van der Waals potential decays of 1 over r to the sixth power. And in the nuclear physics, there's some similar short-range potential where nucleons they interact through the Yukawa potential, which decays exponentially at long distance. So they are all examples of the short-range interactions uh, which features this universal field body physics. So to
Pengfei,
discuss universal field
sorry.
body physics, Mhm.
Just to make sure, here by short range, what exactly do you mean?
Oh, actually, the exact meaning requires uh, the information of dimensionality and the dispersion relation. So for here, let's consider the three dimension. And for three dimension, we require the potential decays faster than 1 r to the cube, 1 over r cube, faster than that.
Uh-huh. And
So actually here,
assuming
all
assuming the
this potential
dispersion,
satisfy this relation, this condition.
assuming the dispersion is quadratic.
Yeah, yeah. Here, I mean, if the dispersion is quadratic, then the condition is 1 over r cubed. But if you change the dispersion, then that the condition can also change.
Okay. Thanks.
Yeah, but when we do theory, one may just imagine the potentials just decays exponentially at long distance. So now let's firstly talk about the two-body physics. So actually, this two-body problem is like the textbook problem. We can find this analysis in many standard textbooks for quantum mechanics. So let's focus on the low energy property of the problem, which means the momentum, the typical momentum in the problem is much smaller compared to the inverse of the potential range, which is denoted as a R naught. And then this two-body problem only depends on the single parameter, AS. So this AS is called the scattering length. We can define the scattering length in many different ways. So for example, we can define the scattering length through this phase shift. So this delta is called the phase shift, and we expand the cotangent delta at small momentum, and the leading order dependence is 1 over KAS. So this AS is a scattering length. So equivalently, one may expand the wave function at a short distance, so which gives 1 minus AS over R. But keep in mind that this short distance still requires this R is much larger than the R naught. So these two atoms are outside the range of the interaction potential.
Question. So,
Mhm.
if the interaction is power law, what is R naught?
Oh yeah, that's a very good question. So when it's R naught, when it's power law, it's actually not easy to define R naught, but you can still compare momentum k to the strength of the potential.
I see.
Yeah. So actually
Thanks.
there are two conditions. I also write one of them. So actually this k momentum should also be smaller to the typical strength of the potential.
I see. Thank you.
So with this scattering length, it actually determines all the properties of the two-body physics. So for example, if we know the scattering length, we can solve the two-body bound state. So the result is as follows. So for a two-body bound state, the wave function is very simple. So outside the interaction potential is just a simple exponential decay with additional factor of 1 over r. And if we expand it at small r, it's, it gives a 1 minus 1 over kappa r. And then we need to compare this expansion to the definition of the scattering length. And then we identify this scattering length is just 1 over kappa. So however, we know this kappa should be positive such that this bound state wave function decays at infinity. So this means we only have a bound state when the scattering length is positive. And the energy, the bending energy of the bound state is 1 over AS squared. And if you can also imagine we have some macroscopic potential with the strength V naught, and we try to increase V naught. Here, let's assume the potential is attractive. So in this case, this scattering length will firstly decay from 0 to minus infinity and jump to plus infinity. And at this point, by this calculation of the bound state, this means there is a new low energy bound state emerges at zero energy. And then if we further increase the potential V naught, the bending energy of the bound state also increase. And there is a special point where this AS is infinity. At this point, we call the two-body physics becomes resonant. And very interestingly, because the low energy property only depend on this single parameter, and AS goes to infinity, means the system becomes a scale invariant. So how to describe such a universal phenomena? A very powerful way is effective field theory. So in the effective field theory, we just replace the original macroscopic potential by a simple delta potential. So this leads to the second term. And using this effective field theory, we can calculate the scattering amplitude by summing up all these ladder diagrams. And the result is also related to so-called the phase shift. And using this calculation, we can determine the relation between this macroscopic, this coupling constant in the effective theory, this little g, and the physical parameter as, and also capital lambda, which is a cutoff of this theory. So this is the relation like this is known as a renormalization relation. So if we put all these ingredients together, we find we have a very complete understanding of the problem. So we have the physical parameter, the scattering length. We know how it's related to the coupling in the effective field theory, which is G. And we know how this physical parameter how this physical parameter predicts the spectral of the system. So which means the bending energy is minus 1 over AS square. So that's the complete information of the two-body sector. So after learning the two-body physics, the next step is go to the three-body physics. So the
Sorry,
first
excuse me.
important
Before
part.
that,
You please.
I want to ask how do you get this renormalization relation? I mean, what does it
Oh,
represent?
Actually, the renormalization relation means using this effective theory, we sum up these ladder diagrams and to obtain the scattering T matrix. And this formula will depend on this coupling constant G, little g, and also this cutoff capital lambda. And at the same time, it is known that this scattering T matrix is related to the phase shift through this formula. And the phase shift is expressed using this scattering length. So this is a physical parameter. So by comparing the result computed from this effective theory and the prediction from the phase shift, we can identify the relation between AS and the coupling constant G and the capital lambda.
But in this process, um, do you have any renormalization process?
Oh, here renormalization means when you do this calculation by summing up the ladder diagram,
Oh, okay,
you need
I
to
see.
take a cutoff.
Okay, I see, I see.
So here,
Thanks.
let's take the simplest viewpoint of the renormalization.
I see, I see. Thanks.
Sorry. Could you please explain a bit more about why do we view this as a effective theory of the model
Oh,
we introduced before?
uh, actually, so the macroscopic problem, so like the original physical problem is like you have a van der Waals potential or you cover potential. So however, you are not interested in the details of this potential, which actually matters if you consider the high energy physics. Like if you consider some energy scale, which is comparable with the depths of the potential. However, if you only focus on the low energy property, it's covered by a single parameter scattering length. Then in this sense, you replace the original macroscopic potential by a delta potential. So which also only contains a single parameter G. So through this process, you throw away all the details of the macroscopic potential, like whether it's a van der Waals potential or it's a Yukawa potential. You just focus on the low energy property to have an effective theory to capture the effect of the scattering length.
Oh, thank you.
Mm. More question? Or maybe okay, maybe I go on. Okay, so that's a two-body part. So
Oh,
now let's consider
sorry. Maybe still a naive question. Actually, I didn't fully get from a physical picture, how does this resonance emerge out? Are you just describing that the bound state becomes unbounded, like at the zero energy window, then you see such a infinite scattering length, something like that?
Oh, actually, that's one phenomena. So this means if you look at all the low energy states in the problem, so all this low energy states only depend on this single scattering length. And actually, not only determine the bound state, it also determines the low energy scattering states. So here, for the bending energy, I only want to present an example of how this scattering length determines the low energy property. So actually, it determines the complete low energy property of the two-body sector.
Okay, I see. Thanks.
Okay, great. So let's consider three-body sector. So three-body is much more complex. So for example, most of the textbooks for quantum mechanics does not discuss this three-body problem. But the first important question is, does the three-body problem requires a new low energy parameter? Because at the two-body sector, we know only one scattering length can describe the low energy property. So if we go to the three-body sector, whether we need new parameter. So actually, the answer to this question depends on the physical system. So at the two-body sector, it does not distinguish whether the two atoms are fermionic, one spin up and one spin down, or bosonic. However, at the three-body sector, these two different types of the system will be different. So this is due to a celebrated phenomena known as the Efimov effect. So it predicts that if you consider identical bosons in 3D and study the three-body spectral, and there will be an infinite number of three-body bound states at the two-body resonance. So here, two-body resonance means A goes to infinity. The scattering length is infinity. Along this line, we have an infinite number of three-body bound states. And also, very interestingly, so the bending energy of these three-body bound states form a geometric series. So this also indicates there is a discrete scale invariance. So more precisely, in the two-body sector, if you do the calculation, when AS goes to infinity, you know there is a continuous scale invariance. However, if you go to a three-body sector, firstly, there will be a bound state, even at AS goes to infinity. And this bound bending energy means your system has an energy scale or a length scale. So this means the continuous scale invariance already be broken. However, because these all bound states form a geometric series, there is still a discrete scale invariance in the system. So this is a very interesting phenomenon. So
Sorry,
how to understand this? Okay.
can you explain the meaning of this figure?
Oh, sorry. So here, this figure, the horizontal axis means the inverse of the scattering length, and so the vertical axis is like the energy of the spectral, the energy. So this means so this shaded region means there are scattering states. So they are not bound states. So here these lines are the location of the bound states. So for example, as this AS goes to infinity, there are infinite number of bound states, and they form a geometric series. So their bending energy form a geometric series.
Then what's the difference between the three-body scattering continuum and the particle-dimer scattering continuum?
Oh, that only means here is a scattering state between the two-body bound state and the additional third atom. And this three-body continuum means it's a continuum state between three atoms. They're just different states, but they all continuum, so there are no bound state in these regions.
Thanks.
Mhm. Okay. Okay, so we need to have a better understanding of this Efimov effect. So let's still get back to the effective field theory. So the idea to write out the effective field theory for this three-body problem is firstly perform a Hubble-Stronovich transform. So if you do not look at this red term, so these first three terms, they are just the Hubble-Stronovich transform of the original effective field theory to the two-body problem. And this D field is called a dimer field. It just represents something like a molecule, right? So it contains two atoms. And now, if you want to consider a new term for the three-body scattering, we need to add the interaction between the dimer field and the atom field, which is this red term. So here, this red term means the scattering between the D and the psi. However, D is a dimer field, it contains two atoms. So actually, this is a three-body scattering in terms of atoms.
Pengfei, I
And
have
you,
a question.
Mhm,
So, in three spatial dimensions, and if the dispersion is quadratic, yeah, suppose
mhm,
we go back to the case where we do consider the interaction with dimers,
mhm.
then that four-body interaction is already RG irrelevant with respect to the non-interacting fixed point.
Uh, I believe you mean perturbatively
Yeah, yeah,
is
yeah.
your terms.
Perturbatively is
Yeah,
irrelevant.
yeah, yeah,
And
yeah.
you choose to keep this irrelevant term without keeping other irrelevant terms. I think the reason is because this is the most relevant one among the irrelevant terms.
Actually, another, yeah, that's maybe one perspective. But I hope to emphasize 2 points. The firstly, uh, when we do this calculation in the two-body sector, actually the calculation is exact. It's not perturbative. So here, actually, when we sum up this ladder diagram, they are the only diagram that appears when we consider only two atoms. So we are doing some exact calculation instead of some approximation. So secondly, we can have higher order terms. So for example, we can also add the three-body terms here, but they will not contribute to the two-body sector. Another possible term is like we add some gradient to this formula. However, that term also contributes subleadingly. So like this, that will contribute to a additional term that is like plus k, so the subleading term in the expansion of the phase shift. So in this sense, these terms are also subleading, consistent with the RG calculation. However, we can do, we can do exact calculation to show they are subleading.
Mhm.
Yeah,
But
so that's why I like a few body problem. All things that can be calculated exactly.
they can be calculated exactly in effective models.
Oh yeah, yeah. In effective models,
And
yes,
here, the reason why these diagrams are the only diagrams, that's because there's no antiparticle, right? Otherwise, even at one loop, there will be three diagrams. Here, there's only
yes,
one diagram.
yes. Yeah, exactly. So we are considering the exact the exactly the two-body problem. So that means we are this is a non-relativistic action. So we have a particle number conservation, right? We do not have a antiparticle, and we also considering the background with no particle filling. So the only particle in this problem is a particle coming inside, so from the left-hand side. So that's the only
Mhm.
particles in the problem.
I'm asking this because then you were talking about including the effect of interaction with dimers. And
Hmm.
in this new effective theory, I think multiple interactions are also irrelevant. Then how do you decide which terms to keep?
Oh, that's a good question. So actually, at the perturbative level, it's not obvious whether we need to add it or not. One example is that perturbatively, there actually no difference between the mass balance fermion and the identical bosons if you just do the dimensional counting. However, the result is different. So for the identical bosons, you need to add this additional term to make the system make the theory renormalizable. So actually, this I think it's just a non-perturbative. You cannot obtain the result using the dimensional counting.
Hmm. But suppose the previous work didn't have so much understanding from the exact calculation. Suppose I directly use the effective field theory, then what is the underlying principle what's the guiding principle that tells me which terms to keep?
Yes. So if you just forget this last term, you do all the calculation using first three terms, and then what you observe will be if you calculate the three-body spectral, you will still find some bending energies. However, if you change the cutoff, the bending energy will also change. So this means your bending energy will depend on the cutoff of the theory. If you want to do the renormalization. This means you need to add additional parameter and tune how this parameter depend on the cutoff to make the whole spectral independent of the cutoff. Then you need this parameter. But otherwise, you can still get the spectral, but the only problem is that the spectral will be cutoff dependent. So that can be directly tested numerically.
Mm-hmm. Let me just make sure. So now suppose I don't add additional parameter and
Yes,
I have a cutoff dependent spectrum.
yes.
Now my question is whether the relation between the different values in the spectrum, meaning different eigenvalues of the different eigenenergies of the bound states, whether their relation changes depending on
Oh,
whether I
you
choose the
mean the
parameter.
discrete scale invariance? The relation?
Yeah, for example, whether they still form the geometric series.
Oh, yeah, they still form the geometric series. Actually, one understanding is that because even if you put additional parameter, there is a renormalization relation. It is possible that you choose some new low energy parameter such that at the given cutoff, your new parameter h is exactly zero. Then your calculation just correspond to that special point.
Yeah, yeah.
Yeah.
And then what's the lesson here? The lesson here, I think one of the lessons is that including the one more term gives me a more general understanding. And I think you are also saying something else.
Oh, including the term. Firstly, I think one question is whether you want to do this renormalization, whether you want to have a effective theory that your spectral does not depend on the cutoff.
Yeah, what's the
So
problem here? It depends on the cutoff.
um, if it's depend on the cutoff,
My coupling constants also depend on the cutoff. Uh,
oh, but the low energy property does not because the coupling constant, yeah, the coupling constant that, depend on the cutoff. But this combination, I mean this two-body T matrix after the renormalization, it does not depend on the cutoff.
Yeah, but even if I don't include one more term, maybe the renormalization relation is just more complicated.
Uh, you do not have new parameter to renormalize, right?
Oh, I see. You mean at low energies, I do need two parameters.
Yes. Yeah,
Uh-huh.
that's exactly the problem. You need two parameters. You need to add one more in order to cancel the dependence on the cutoff.
I see, I see. Then from the physical picture you just presented, one of the parameters is still the scattering length, and the other is the S0.
Oh, sorry. The S naught is S0 is just some number, so it's not a parameter. It's some number like 1.00624.
Oh, it's a
Uh,
universal
but
number.
the other parameter is
Mhm.
like the bending energy of some state. For example, this E naught. You
I
can
see.
just this E naught is some parameter. But yeah, I will define my parameter more precisely in later slide.
But just to make sure, as you said, even if I don't include the other term, I still have the bending energies still form the geometric series.
Yes,
Then
that's
I
right.
can, in principle, use.
Yeah, you can use that to do some calculation, but at that time, your E naught is like it's a capital lambda square, so you cannot tune it freely.
I see. So that's
If
like
you want to
some
fix the
fine-tuned
cutoff, if
result.
you want to, if you also if you are also happy with tuning the cutoff, then I think that's okay.
Mhm. Okay. I think now I understand. So
Mhm.
basically, if I go to the next slide, I can
Mhm.
either say I consider the theory with an infinite cutoff, then the couplings are G and H, or I can say I consider a system with a finite cutoff, then the parameters are G and cutoff.
Oh, exactly. Yeah, that's right.
Thanks.
That's right. So okay, mm, so with this new effective theory, we can do some calculation for the three body problem. So like we can calculate the scattering between one atom and one dimer. So that corresponds to the scattering between three atoms, right? Because the dimer corresponds to two atoms. And the diagram for this three-body scattering is also very simple in terms of this atom dimer picture. So actually, this is the reason to introduce the dimer. So otherwise, you need to have three incoming atoms, three outgoing atoms. That the diagram will be more complicated. So now, using this very simple set of diagrams, you can write out the equation, so which is called the STM equation. So this is uh, how it looks like. So I will not present the details of deriving it. I will just present the final result. So this is the STM equation. So here we assume the scattering length AS is infinity, and we are also considering the three-body bound state. So for the bound state, we assume this three-body scattering amplitude can decompose into the wave function, the bound state wave function phi, and also contains a pole when this E approaches some binding energy En. So then we obtain this equation, this STM equation for bound states. And firstly, we can do some dimensional analysis. This H, which is a new interaction term, has a dimension of -2. So we can introduce the dimensionless coupling constant as this capital H. So secondly, this equation, since we have already set AS goes to infinity, it has a continuous scale invariance. So for example, if we simply set capital lambda goes to infinity and energy E equals to 0, so this equation becomes scale invariant if you do a transform. So more precisely, let's look at the solution as follows. So let's separate the domain of momentum k into three different regions. So one region is that the momentum k is more or less the same as the square root of energy E. And another region is that the momentum k is more or less similar as a capital lambda, which is the cutoff. And there is another regime called regime B, where the momentum is much larger than the energy and much smaller than cutoff. So if we assume this kernel has some locality, which means it decays sufficiently fast when this K and Q differs from each other. And then we can solve the eigenfunction in this regime B by setting this E goes to 0 and capital lambda goes to infinity. So this becomes a very simple equation because after setting E goes to 0, lambda goes to infinity, so this equation is actually scale invariant as discussed in last slide. And the integral equation that is scale invariant has a very simple solution, so which is just a simple power. And you can determine this power S by plugging this ansatz into the integral equation. And actually, for the problem of the Efimov effect. So this S is complex. So it can be -1 plus minus I S naught, where S naught is determined by this equation, this equation, which can be solved numerically, giving S naught equals to 1.00624. So this is a very famous number in the field of the field body physics.
Pengfei, can you remind me what is lambda?
Oh, lambda is a number. Sorry, it's just a
Oh, okay.
number. That's
Mhm.
Yeah. But for now, if you only look at this region B, we can now decide how these two different solutions with plus or minus sign can superpose. So in general, we
Excuse
can.
me, sorry.
Mhm.
So how can I see that this equation is related to the problem we are discussing? So can I derive this equation from the setup we are introducing?
Oh, you mean this equation?
The equation that determines S naught.
Oh, this equation? Oh,
Yeah.
this just means the way to determine S naught is to plug this ansatz, this phi equals to k to -1 plus I S naught into the equation above. And then
I see.
this equation gives some number, some equation for this number S naught. Yeah, that's a way
Uh,
for deriving it. Yeah.
so it is based on the ansatz of the scale invariance.
Yeah, because in the region B, it satisfies such a equation. This equation is scale invariant because it's obtained by the previous equation, and cite this capital lambda goes to infinity and E goes to 0. Then this system contains no length scale because the AS is infinity, the energy is set to 0, and the cutoff is infinity. There is no length scale. So the equation is guaranteed to be scale invariant.
Thank you.
Okay. So, but now we will obtain these two of these solutions, the k to the power of -1 plus minus is naught. So this plus minus is naught is actually like cosine s naught ln k or sine s naught ln k. But we need to superpose them, these two different solutions, to obtain the general solution in the region B. So, however, without the knowledge of the solution in the region C, we cannot determine this superposition factor. So instead of doing that, let's introduce this parameter as a three-body parameter. So this is a new parameter in the three-body physics. So actually, this is very similar to the two-body problem. If you still remember, when doing the two-body physics, we can define the new parameter as a superposition factor between this solution 1 and 1 over r. So here is something similar. So, but here is defined in the momentum space. So here, this lambda star is the new scattering parameter. And now we already know the solution in B with this parameter capital lambda star. Then the problem becomes solving the wave function with the boundary condition in B given by this cosine s naught ln k or lambda star. And in this sense, we can send the capital lambda goes to infinity because the effect of capital lambda already included in the lambda star, and solve the problem using region A and region B. And if we look at these two regions, the equation is invariant under the rescaling of the momentum, and together with a rescaling of the energy E. However, at the same time, you need to satisfy this boundary condition. For this boundary condition, it fixes a proper superposition between the two solutions. So this rescaling should be compatible with this boundary condition. This determines that this A can only be a factor of e to the pi 1 s naught. So this means we cannot do the scale transform for arbitrary A, which corresponds to the continuous scale invariance. So here we only do the scale transform with this A equals to pi over S naught. So this corresponds to the discrete scale invariance. And using this relation, it also determines that the eigenenergy is En from a geometric series. And this factor is just A to the minus 2nth power. So this A is just e to the pi over S naught. So this explains why this infinite number of a three-body bound state emerges. Although we solve this, we can solve it in the three-body problem. Actually, the Efimov effect had very broad implication in the many-body physics. So, for example, it can be observed in the many different peaks correspond to the Efimov states can be observed in the atom laws in the cold atom physics. And also, this Efimov effect also implies there is a large log periodic oscillation for the momentum tail. So actually, this is easy to understand because it's wave function in the momentum space decays with additional log periodic oscillation. So this means if you measure the momentum of the atom, there will be a log periodic oscillation. And also, you can study some problem called the Bose-Polaron in the cold atom system, and you can also observe the effect from the Efimov effect.
Question?
Mm-hmm.
Does the Efimov effect also exist in 1D or 2D three-body systems?
Very good questions. Actually, this is related to the second part of my talk.
Okay.
In the traditional problem, like you have a kinetic term, which is p squared over 2, it does not appear.
Mm-hmm.
So I will give more comments later
Okay.
in the second
Thank you.
part.
Thank you.
Very good question.
Hi, I have a question. So,
Mhm.
does the effective field theory we have now allow us to derive the continuous states?
Oh, it allows to the calculation for all the low energy state, including the scattering state. But yeah, but not using this STM equation for bound state, because this STM equation for bound state is already a homogeneous equation, because we have assumed the energy E is close to some binding energy such that this three-body T matrix has a pole structure. If you want to calculate the scattering matrix or scattering state, you need to go back to this equation. So there will be a inhomogeneous term. So if you add back this all inhomogeneous terms, you can determine the scattering states.
What do you mean by inhomogeneous terms?
Oh, so here this equation like T3 equals to this diagram plus this diagram plus some kernel times T3 and some kernel times T3, right? These
Yeah.
last two terms. And these two terms are they all include T3, and this term include T3. So, and if you only keep this, the left-hand side and these two terms, so everything is proportional to T3. So this means it's a homogeneous integral equation. So, but now it contains the two additional diagrams. These two additional diagrams does not contains the information of T3, right? They're just simple diagrams. So this equation becomes inhomogeneous.
Oh, I see. Thank you.
Mhm.
I also have one more question, Pengfei.
Mhm.
I
Sure.
think I asked, but let me ask again.
Uh-huh.
So how do we make sure, for example, in the three-body problem, there are only two parameters? What if there are more that we didn't know?
Oh, yeah, good question. But then I think the way to solve it is like we try to make sure the all low energy observables, we can do the calculation. We can check whether they indeed are independent of the cutoff.
Mm-hmm.
The good thing here is like we can actually do the exact calculation, so it's more or less easy to know whether they are enough because we know the solution in some sense.
Yeah,
For
but
more general cases, maybe.
if we don't know the solution from the beginning, I guess it's hard to know, right?
I agree. Yeah, I agree. Uh,
Mm-hmm.
I think it's like after people learn from Vitaly Efimov that there is an Efimov effect, then people realize that we need to add this three-body parameter. I think that's a historically that's a way how people realize it.
Uh-huh.
It's not so obvious actually.
Yeah. And in principle, one could ask whether in the future someone else will discover some new effect which requires another
Hmm.
parameter. But I guess you are saying based on the understanding of this problem, based on the more or less exact solution of this problem, there's no new parameter.
Yeah, yeah. One is the exact solution. Another, actually, people do very high accuracy numerics that can also be used to test whether new additional parameter are required, right? So like we
Mhm.
just change the cutoff and fix all the renormalization relation. We look at the low energy property whether they change when we change the cutoff.
Mhm.
Yeah. So I
Okay.
think both analytical solution and also numerical study.
Mhm. By the way, for analytic solution, what do you mean? The three-body problem, even for classical system, is not analytically solved.
Yeah, that's a very interesting question. So yes, that's a good point. But actually, um, as we will see, this equation, when this energy E is much smaller than the capital lambda, this equation is solvable. You can obtain the exact solution of this wave function phi. So that's quite amazing. So actually, that's one of our main result. So.
I see, I see, I see. So basically, although in general the three-body problem in the quantum setting is not solvable, but in the knowledge regime it is.
Um, Firstly, in general, for example, here, I think that in quantum mechanics, it can always be written as a linear equation, right? So it's a linear equation with like three variables, or like field body physics is like a set of integral equations. In this sense, you can always do numerical simulations of these equations. But
Uh-huh.
for the three-body problem with this effective theory, we can do better. We can do the analytic solution.
For the knowledge physics or for any energy scale,
Sorry?
for any energy scale or for small energy scale.
Oh, for small energy, when this E is much smaller than cutoff. So we are still imagining this cutoff is sending to infinity, not like that.
I see, I see.
Mhm.
So if you send the cutoff to infinity from the beginning, then is it possible to solve the equation for any energy?
Then if you set it to infinity at the beginning, then the solution of the wave function is not well defined actually. And
Oh,
the reason is that this capital lambda star should depend on lambda, right? So there's a
uh-huh.
renormalization relation. So, sorry, I should not. I mean, there is a renormalization relation between this H capital lambda and this new parameter capital lambda star. So if you set one of them to infinity, then and also if you keep this H fixed, then there is no well-defined limit for this lambda star. So
Okay.
yeah,
Mhm.
yeah, that's one problem. When doing this calculation, if you want to obtain the exact renormalization relation, you need to solve this equation with lambda. So that's
Mhm.
why it's not so easy.
Uh-huh. I see. Thank you.
Mhm. Okay, for now, let's recall what we know up to now. So like in the two-body case, as I explained, we have a very complete understanding. Like we have a two-body parameter, we have a coupling constant G, we have their renormalization relation, and we have a binding energy E, we have this relation. However, in the three-body case, although I have tried to explain why there is an emergence of the Efimov effect, however, I have not discussed how this coupling constant H is related to the capital lambda star. And I have not explained how this bending energy kappa star is related to the lambda star. So let's maybe I forgot to emphasize this kappa star is defined by the prefactor of the bending energy. So how this kappa star is related to the lambda star is unknown for now. But these two questions they are quite fundamental. So we cannot be the first people to study them. So the first study on this renormalization relation can be dated back to the 1999. And the assumption is also very straightforward. So although we derive such a wave function for regime B, so in this paper, they simply assume this form of the wave function is also valid for regime C. And then if they do assume this, they can do the integral directly for the left-hand side around the capital lambda and obtain how the left-hand side depend on the capital lambda. Then they can tune this little h, tune the dependence of the little h such that it cancels all the dependence of the capital lambda on the left-hand side. So then they determine the renormalization relation. So just by direct doing the integral. So this leads to the following result. So we still write everything in terms of this capital H, so which is related to the little h by a simple lambda square. So this is a relation. And in terms of this capital H, the renormalization relation is like 1 plus S naught tan phi over 1 minus S naught tan phi. So this tan phi, this phi is the S naught ln lambda star over lambda. So I think this is a first analytical study of this renormalization relation. And later, people try to do some numerics. So firstly, they find the renormalization relation obtained in numerics contains an additional numerical factor. So after adding this factor, the theoretical prediction matched the numerical analysis to very good accuracy. However, this looks like a random magical number. It's 0.879, right? It's a very magical number. Secondly, they also study the second question on the spectrum of the system. So they find also numerically that this S naught ln lambda star or kappa star is around 0.971. Okay, so there are two magical numbers in the problem to be understood. So basically, our result is that we solve both these two questions analytically. So here, let me first present our result. So firstly, we derive the exact renormalization relation expressed in this formula. And here it contains a parameter like alpha and phi naught. And this alpha can be expressed as an integral. So this f is some known function. So although it looks very complicated, this means we can just do some integral, for example, numerical integral, to obtain the value of alpha. And if you do it using like Mathematica, the result is just 0.87866, and you can obtain obtain the result to arbitrary accuracy if you like. So this matches the numerical study to very high accuracy. Secondly, our result contains this new factor of phi naught. So actually, this is a problem in the numerical study. So in the numerics, they define this phi through the fitting of this relation. So they absorb the definition of phi naught into this lambda star. So their lambda star is the definition actually different from our lambda star. And as a result, they do not find this additional shift in phi naught. And we can also determine this phi naught, which is like 0.05. And actually, this phi naught is important because we can define this lambda star through the behavior of the wave function. this is more similar to the two-body problem. We need to determine the low energy parameters through the low energy behavior of the wave function. So then after fixing this definition, so this find out is very important. Secondly, we find the exact relation between the lambda star and the kappa star. So which is a rather simpler formula. However, if you do the if you calculate it numerically, it gives you 1.018. It's about 1.02. And actually, if you compare this 1.02 and 0.05, if you subtract this number, subtract the phi naught from this number, you obtain 0. Sorry, a minute. 什么是？先放这儿吧，我在讲啊。您一会儿帮我把这门关上。Oh, I'm really sorry. Okay, so if you look at these two numbers, their combination is just the numerical result. So this 0.971. The reason is just because they absorb this phi naught into the definition of lambda star, which also shifts their relation of the bending energy. So this means our result is consistent with all previous numerical calculation. And we also performed our numerical calculation to very high accuracy. And so here, this red line is the analytical result. And this dashed line is the result in the literature without this phi naught. And these data points are from our numerical calculation. We see the numerical result and the analytical solutions match to very good accuracy. And for the binding energy, we also observe that if the energy is low enough, so for example, this second branch of the solution, they already match the analytical solution to very high accuracy. So let me remind you that here this relation for the bending energy is in the low energy limit. We'll assume the energy E is much smaller than capital lambda. So however, in the numerical simulation, there will be some bound state which has an energy comparable to capital lambda, which is these solutions. So their bending energy deviates from the analytical prediction. However, as long as the energy decreases, for example, the second solution in the numerics, so they already match the analytical solution to very high accuracy. So let me briefly mention the idea to find these exact results. So let's still look at this cartoon for the three different regimes for this solution of the wave function. We have regime A, regime B, and regime C. And if we want to obtain the renormalization relation, so recall that renormalization relation is something at high energy or high momentum, right? So if we want to obtain the renormalization relation, we need to focus on the high momentum regime C. So this means we can solve the STM equation in the regime B plus C. On the other hand, if we want to answer the question on bending energy, we need to focus on the interplay between the momentum and the energy E. So we need to focus on the low energy behavior, so which is in the regime A plus B. And we already know there's a boundary condition in the regime B that is determined by our definition of the capital lambda star. So this serves as a boundary condition when solving the problem in either A plus B or B plus C. So firstly, let's look at the renormalization relation. So for the renormalization relation, we can safely neglect the contribution from a small momentum. So we just assume this energy E is zero. And another important observation is that, so our equation is it contains some scale invariance. So instead of original momentum variable k, we can introduce additional variable t by adding an exponential function. Then, using this exponential, after this introducing this new variable, the original scale invariance becomes a translational invariant, right? So then this kernel is only a function of t minus s. However, importantly, this equation is still very hard to solve. One main reason is from this zero. This integral is from 0 to infinity. It's not from minus infinity to plus infinity. So if it's from a minus infinity to plus infinity, solving this integral equation, we can just use some Fourier transform, right? Then we get the solution. However, it's from 0 to infinity, so this makes the solution of this equation very hard. Fortunately, this is not a new problem. So actually, in mathematical literature, this type of an integral equation without this h term has been well studied. It's known as a van der Waals integral equation. And this type of integral equation can be solved using analyticity of the function. So what we did is to generalize the van der Waals integral equation, the method to solve this set of integral equations, to include the effect of this capital H. And then we can get the general solution of C, so which is just a wave function. So this is the basic idea for our analysis in the theory. So I will not get into the details, but now let's just mention the idea to solve the second part, the bending energy. So for the bending energy, we analyze the regime A and B. And when we focus on A and B, we can safely set capital lambda goes to infinity. And very amazingly, this STM equation can be solved exactly and actually very easily by introducing a new set of variables, tau, so which is related to original momentum k by our arc-cinch function. After performing this transformation, the equation is as follows. So there is a kernel k, and integral is also from 0 to infinity. However, this form of the kernel k is very special. It's a function of tau minus sigma and a function of tau plus sigma. So this the difference between these two functions. And using this special form, we can actually extend the definition of the wave function c by performing the anti-periodic boundary condition. Sorry, we can perform a reflection with additional minus sign. And then this c satisfies the integral equation from minus infinity to plus infinity. And then this can be solved using the standard Fourier transform, and the solution is also very simple. So the exact solution is just given by a sign S naught tau. Since tau is related to the momentum k, we can expand this solution at large momentum k and compare it to the boundary condition fixed in the regime B. And then that determines the relation between this energy E and the capital lambda. So this leads to this result for the binding energy. And in principle, we can apply our exact renormalization relation to study various problems, including all these problems, and to provide a better or more awkward result for their predictions. So, okay, so in all previous discussions, we consider the effective field theory where we put a sharp cutoff for the momentum. So this is just one way of doing the regularization. So however, in the numerical simulation, sometimes people considering more general regulation functions. So in this paper, in collaboration with Barra, who is actually the author in the paper of the paper in 1999, the first paper for the renormalization relation. So we obtain a general form for the renormalization relation for arbitrary separable regulator. However, in this case, this alpha, C, and phi naught, they are just parameters to be obtained from numerics. However, we can show that this functional form is valid for very general class of regulators. Okay, so this is the first part of my talk. Is there any question?
I want to ask one more question. I think is the question is about a comment you made. I didn't understand it when you made it, but I just want to confirm whether I understand it now. The comment you made about for example, in the simplest case with only two particles, I was asking the contact interaction is RG irrelevant, and then you said this is not Paul counting. I think is the following understanding correct? Here we want to understand the knowledge physics, not only including the non-interacting fixed point, but also potentially another fixed point, which is the AS equal to infinity fixed point. If I want to use a single Lagrangian to understand both fixed points, then I need to include the G term.
Mm. Yeah, I think that's a good understanding.
Okay. Yeah, that's what I want to confirm. Thanks.
Okay.
And similarly for the three-body case, to understand the different fixed points, including the non-interacting one and the AS equal to infinity one, we also need to, as you said, we need two parameters.
Yes.
And if we want to use a single Lagrangian to describe both fixed points, then it takes that form. I see.
Okay. Yeah, I agree. That's good understanding.
Thanks.
Okay, so this is the first part of my talk. So it's like obtaining some exact relations for the old problem. So now let's come to the second part, so which is more closely related to the new developments. So they're also related to the previous question. So Efimov effect, as I mentioned in the previous slides, are all focusing on three dimensions. But recently, there are many experiments, like the cold atom experiment. We can prepare a system in lower spatial dimension, so like using optical lattices. So does Efimov effect exist in lower dimensions? So if we want to have a system with Efimov effect, it at least requires two things. So firstly, the two-body sector should be scale invariant. So because we hope to have a discrete scale invariance three-body sector. So this is only possible if the two-body sector has a continuous scale invariance. So secondly, we hope the system contains an infinite number of bound states. So it's better the system to be strongly interacting. If we have a non-interacting system in the low energy limit, we do not expect it contains infinite number of three-body bound states, right? So that's a two physical requirements. So in 1D, if you compute the phase shift of the system, so it's given by cotan delta equals to K A1D. So A1D is like the one-dimensional scattering length, which is very similar to the AS in three dimension. So where is the two-body resonance? So if we want to ask where is the two-body resonance, it's again at AS goes to infinity, right? So when AS goes to infinity, the binding energy is 1 over AS square, which is 0. However, when AS is infinity, this is actually, this cotan delta also diverges. So this means the system is actually in a non-interacting regime. So if you still remember, the two-body T matrix is proportional to 1 over cotan delta. So here, this formula. So when the cotan delta diverges, this means the system is actually non-interacting. So this means the system cannot exhibit the Efimov effect. As a comparison, so in the 3D, when AS goes to infinity, the cotan delta becomes 0. So the system is actually strongly interacting. So actually, in the previous studies, people have do the analytical continuation for the dimension D, and the result shows that the Efimov effect only exists when this D is larger than 2.3 or smaller than 3.8. So this means the only physical dimension that exhibit the Efimov effect is the 3 dimension. But now, recently there are very rapid development of quantum science and technology, and we have more types of quantum systems. So for example, in trapped ions, we have it is described by some quantum spin chains with long-range interactions, which decays of 1 over r to the alpha's power. So this alpha is actually tunable, so which can be very small and can be very large. And we also have the Rydberg atom array, where the spin-spin interaction decays either 1 over r to the third power or sixth power, so which correspond to a dipole-dipole interaction or van der Waals interaction. So comparing to the quantum system I described in previous slides, so now we have a spin system. It's not a system for particles. However, for the spin system, we can have quasi-particles like magnons. So it is possible these magnons form some interesting field body states, just like the atomic particles, just like bosonic atoms. So this is the basic idea of our study in the second part. So to be concrete, let's consider a long-range spin chain with this Hamiltonian. So here, firstly, we have a xx plus z, yy term, and second term is a zz term. And we see we choose the model such that the model is invariant and the rotation along the z direction. Actually, we can view this model by mapping it to a model for bosons. So firstly, the system has a rotational invariance along the z-axis, which means the total magnetization along the z direction is a good quantum number. And this is very similar to the particle number conservation for atomic physics, for the atoms. And then when we compute the field body problem for the atoms, we choose a vacuum state as a reference state and using this creation operator to create bosons. And similarly, in the spin model, we can choose the fully polarized state as a reference state. And then we can create the excitation by applying this lowering operator, the sigma minus. So in this cartoon, you can imagine all these spin downs are particles, so they are just the magnons. And for this system, it contains 3 magnons. And there is a 3-body problem of magnons in this long-range spin system.
Pengfei, why do you only consider long-range hopping but not long-range density-density interaction?
Oh, that's for theoretical simplicity. The reason is that we want to have some analog of the short range interacting problem as for the non-realistic particles. So in that case, we assume the potential V is short range.
I see.
So here, similarly, this, as we will see, this J term corresponds to the scattering between magnons. So we hope this also a short range interaction potential.
But experimentally, suppose I want to engineer this model. Is it
Yeah.
easy to make the XY term long range, but XZ term short range?
Yeah, in principle, that's possible. The reason is that both long-range coupling and also short-range couplings has been realized in trapped ion experiments. So in principle, we can prepare we can use some lasers to create this long-range coupling in the x direction and the y direction, and use another set of laser to create this coupling in the z direction. But I agree that maybe this is harder than considering the long-range interaction in all directions. But in principle, it's possible.
I see. And here is it important for J to be positive?
Oh, that's important because we'll be talking about the three-body bond state. So, so the G is positive means the magnons has attractive interaction, so they can form bond state.
And when
You
J
can
is
also,
positive,
if it's positive, sorry, if it's negative, maybe you can also consider some repulsive bond state. That's maybe possible, but I have not worked out the details, but that's more possible, I think.
yeah, and when J is positive, then the reference state is very simple. But when J is negative, the reference state, I guess, is pretty complicated.
Oh, sorry, but this I mean this model has a rotational invariance along the state direction, so you can always choose a reference state as all as a things polarizing to the up, or you can also choose it as all spin polarizing to the down direction.
No, I mean, if both JZ and J are negative, then even if it's short-range interaction, even if its Heisenberg model is complicated, it's still conformal field theory.
I mean, we are not studying the like half filling ground state. We are studying the physics in the near polarized sector. So I think this is a little different. We are not talking about this omega is a ground state. It's just a fully polarized state.
Oh,
It
I
do not
see.
require it's a low energy state. Yeah.
For example, it can be it might be the highest energy state.
Yeah, it's possible. Yeah.
Okay.
Yeah, because it's a rotational invariance, so it's not really important. At least theoretically, it's not important.
Hmm.
Yeah, experimentally, yeah, I agree. Maybe that will lead to some loss, maybe. Yeah. Okay, so before talk about the three-body physics and the two-body physics, let's firstly consider the single magnon sector, which already explains why this system is very different from the traditional system with non-relativistic particles. So let's consider the single magnon excitation, which means we just flip one of the quantum spin. And this XX and YY term, we can write it in terms of sigma plus sigma minus, and this leads to the hopping of the magnon. And actually, because this x, y, x and y term are long range, so this is a long range hopping. We can consider the eigenstate of the magnon, which is just very simple. It's just a momentum, uh, the states with a fixed momentum. And the single particle excitation energy is also very simple because we know if the particle hop from 0 to r, it leads to the energy like cosine kr. However, there is a probability distribution for this r, which is long range, and we only need to sum up all these contributions. So this is a final result for the single magnon excitation energy. And we can expand this final formula near k equals to 0 to ask the low energy dispersion. And this is a very interesting result, but actually it's just a universal for long range coupling systems. So when this alpha is smaller than 3, the leading order contribution is from k to the alpha minus 1's power. So this means when alpha is smaller than 3, the dispersion of the magnon is no longer quadratic. So this leads to a new probability to realize the novel field body physics in such a new system. So now let's look at the two-body sector. So for the two-body sector, we need to write some effective field theory. However, the only modification is the single particle dispersion. So the second part, so this part is just the same as a three-dimensional identical bosons. The only difference is from this ipsil k. So now let's assume it's a general dispersion with exponent z. So this z is known as a dynamical exponent. And we can calculate the two-body T matrix and very similar to the 3D boson case by summing up all the ladder diagrams. So this is the result. Then we try to analyze this scattering T matrix and ask whether it can be scale invariant and strongly interacting at the same time. So now let's do some simple analysis. Because this ipsiloid k is k to the z power, we can try to expand the integrand at large q. And the leading order behavior is q to the minus z, and we have additional sub-leading terms and so on. So firstly, if z is larger than 1, so actually this result will, the special case for z larger than 1 is like z equals to 2. So then this will be the same as a non-relativistic particles in 1D. Then actually we can show that when z is larger than 1, all the physics are similar. So they all correspond to having a non-interacting resonant point, and we do not expect the system to exhibit the Efimov effect. And secondly, if z is smaller than 1/2, then we see that these two terms, the first two terms, they all diverge after integrating over Q, right? That means they all contain the lambda dependence after the integration. And if we really want to do the renormalization relation, we need to introduce two different terms here. So instead of this a single parameter g. This is possible. We just revise the effective field theory and add additional terms in the theory, and we can still do the renormalization relation. However, if we add additional terms, this means the low energy theory of this problem contains two parameters. When we have two parameters tuning a single potential, tuning a single depth of the potential, we can only send one of the parameter to infinity. Then in the low energy physics, even at the two-body resonant, we are still left with a single parameter. This means the two-body resonant point is no longer scale invariant. So the system cannot exhibit the Efimov effect. So for both z larger than 1 or z smaller than 1/2, we do not expect the system to exhibit the Efimov effect. So the remaining regime is z larger than 1, 1/2, smaller than 1. And in this case, all the calculation is very similar to the three-dimensional identical bosons, and we can obtain the renormalization relation. And we can also obtain the two-body scattering T matrix. And similarly, if we tune the low energy parameter P goes to infinity, the system becomes a scale invariant. And actually, it's also a strongly interacting fixed point. So this indicates it's possible for us to observe the Efimov effect in this system. And to really show the emergence of the Efimov effect, we again go to the STM equation. And we write out the STM equation and try to solve the wave function in the region B and ask whether we have a non-zero S0. So the right-hand side in this figure, this is our final result. So we find that if the alpha for one-dimensional system, if the alpha is larger than 1.52 and smaller than 1.88, there is a non-zero solution for S0. So recall that this imaginary part corresponds to a log periodic oscillation of the wave function, and log periodic oscillation of wave function gives you the Efimov effect. So this means in this regime, we have the Efimov effect. Indeed, we can extend the calculation to 2D or 3D. We can all observe the Efimov effect. Finally, we also compare our result, our theoretical analysis, to numerical results, either from a numerical solution of the STM equation for the effective theory. We also calculate we also numerically calculate the energy spectral for the original lattice model. That is this quantum spin chain model. And we all compare their prediction of the bending energy to the theoretical prediction. So we find the match to good accuracy. So in addition to the problem with homogeneous nearest neighbor interactions along the z direction, we also study another problem, whereas we assume the interaction only only between the zeroth side and the first side. So this is like an impurity problem. This is the interaction only appears when when two magnons is close to this impurity. And in this system, we on the one hand we find the Efimov effect also emerges in this system on the two-body resonance. And more interestingly, there's another class of novel three-body bond states called the semi-super Efimov effect. So which means the bending energy of the problem, we take a log, it is quadratic in the n instead of linear in n. So this is another very interesting class of universal three-body bond states. Okay, so this is the second part of my talk. Let me first let me do some summary of the whole talk. So here in this talk we revisit the old problem of Efimov effect. On the one hand, we obtain some exact renormalization relations and also energy relations, and on the other hand, we propose the new realizations using long-range quantum spin chains. So in the future, we can try to extend the exact relations to other Efimov systems, and also, actually, we focus on the spectral at the infinite scattering length. We can also ask whether we can solve it at finite scattering length. Actually, we tried, but we do not have very good answer. And secondly, for neural realization, our result indicates there is a very general class of fuel body problems or dilute gas problem in this quantum spin chains. So maybe we can study more interesting fuel body physics in such a setup. Okay, thanks for your attention.
Okay, thank you for the very interesting talk, Pengfei. Are there any further questions?
Thank you.
Oh, just one question. So here you are discussing these two-body and three-body scatterings. I wonder if you have, for example, four-body or even five-body involving in the scattering. Will you have more parameters? Intuitively should be, and how the difficulty will like increase.
Oh, very good question. So actually, one problem is like this. So one problem is that whether if you look at the four-body sector and five-body sector, whether we will expect novel bond states in the four or five-body sector. So for the system with the Efimov effect, actually one cannot ask the question because they are already very deep three-body bond states. So this means you consider a four-body system. All of these regions will be filled by the trimer atom continuum. So they are all scattering states. So we do not expect a new. We cannot discuss the four-body bond state in this whole region. But one related question is for the fermionic case. So for example, we have one spin up fermion and three spin down fermion. And we can compare, we can ask whether they form some universal bond states. We can tune the mass ratio between the spin up and spin down fermions and ask the critical mass ratio for the emergence of of these bond states. And this is this is some, I think it's some important field questions in the field. However, it's very complicated to study this problem. I think up to now people can only study like six-body problem like that. But that's very very hard. You need to do very large scale analysis, and theoretically the equation is also very complex. So I think up to now we do not have a very good understanding theoretically.
I see. Thanks.
Other questions?
I also have a question. So if we consider relativistic particles, what do we expect about the
I think Ying Chen
dimensionality
is speaking, but
where
I
the
cannot hear
Efimov
him.
effect can emerge?
Oh, if it's a relativistic particle, one important difference is that we cannot find the exact equation that governs the field body physics. The reason is that a relativistic particle always has a antiparticle, right? So
Mm.
you cannot write out. So actually, you cannot define what is called the two-body physics or three-body physics because you
Yeah.
also you can always excite some particle-antiparticle pair. So that's one important difference. So in that case, you cannot write out the exact equation govern the field body physics.
I see.
Yeah,
It's,
but I think
I
it will
think
be different.
this also happens if we consider quadratic band touching, something like that, right?
Uh, well, but
There's also
here we are
antiparticle.
considering the system. Um, it's a true vacuum, so we do not have other field band. So you have
Yeah,
so if your lowest band has a quadratic uh, behavior,
yeah. If there's a
then
touching,
but if it's a touching, there's another band, then there will
yeah,
be some field band.
yeah,
Then
yeah,
you can excite a particle antiparticle like this.
yeah. Then there will be
Not
some
a
difference.
true, I mean, this is not a true field system.
Yeah, that's what I was trying to say. This also introduces antiparticles.
Yes, yes.
Mhm.
Uh, but then I'm not sure whether the same Efimov effect appears because this um, so for this Efimov effect, the infinite number of bound states is it's like delicate. So the reason is that the size of the bound state will be very very large if you consider very low energy states. So if you can excite some particle-antiparticle pair, even if the density is low, because the size is very large, so the influence may be important.
Mm.
So
Other
yeah, I'm not
questions?
sure. Yeah,
Mm.
actually, I don't know the answer.
Mm.
Sorry.
Other questions? Oh, then I have some questions.
Mhm.
I have two questions. One about the first part, like on this slide. So, I think my understanding is that you said if I want to consider two particle physics, then I use the previous effective field theory. And if I want to consider three particle physics, I want to use the effective field theory here.
Yeah, if you want to study the three-body physics in the you understand the capital lambda goes to infinity, like you do the renormalization, you need to use this.
Yeah.
You
Uh,
can also use this to study the two-body physics. But the reason is that the last term will not contribute in the two-body calculation.
I see. If I want to use this effective theory to study two-body physics, I suppose I need to make G somehow very small.
Oh, sorry, this G is the same as the G here. So they are just the same factor. They are
Uh-huh.
just the same. So you'll get exactly the same renormalization relation.
Oh, I see. Then, so it means the effective field theory for the three-body interaction just now, it already contains the two-body physics.
Yes, yes. Like you can. So this is a effective action for number of particles smaller or equal to 3 for now. So, but you can also check whether it works for four-body sector and also check whether it works for five-body sector. But for
Mhm.
now, it is guaranteed that this works for two or three, or
Mhm.
three, one, two, three, right?
Mhm. I have another question about the second part. So, uh, you said
Mhm.
one question there is you expanded the dispersion around some k equal to 0.
Yes.
Then how do I know whether the higher order terms in the expansion do contribute other fixed points?
Oh, you mean whether they are important or
Yeah, whether they're
uh,
important in some other regimes.
maybe important in some other regimes, but naively I would expect because we are assuming the lowest field scattering state or like bound states, so we are actually expanding all energy around the lowest energy point. So
Mm-hmm.
yeah, I don't have a better answer, but physically I would expect it's correct. And actually, it's verified in the numerics because in this latest model we use a macroscopic model. It contains all the terms. It does not effective theory calculation. It's a
Mm-hmm.
macroscopic calculation. And
Mm-hmm.
actually, it agrees with the theoretical prediction to good accuracy. And the difference. Uh, I think the difference is only from the fact that I didn't do the discretization very carefully. That can also definitely be improved by improving the numerical method.
Mm-hmm. Another question is, I wonder if you have any comment about the following. So, your z can be is some tuning parameter. If z
Mm-hmm.
is smaller than 1, it means the dispersion, the velocity is divergent.
Uh-huh.
So the information propagation has a very large speed.
Mm-hmm.
Uh, do you have any comment on this? And also, if alpha is
Oh,
smaller than 2, there's no Lieb-Robinson bound. The information propagation speed is also very large. Do you have any comment on
oh,
this?
I don't really have any comment. In our calculation, I don't think I think it does not matter actually.
Mhm.
So we do not observe any singularity at z equals one. Like that.
Mhm.
You mean one or one half?
Z equal to 1 and alpha equal to 2. So if
Z
alpha is
equals
larger than,
one.
if
Yeah, they can all be described by some effective theory. I mean,
mm,
I don't find any. I think it's not so strange for me. For me, at least from the perspective of field body physics, it's just some well-defined theory.
mm,
Yeah. Not sure.
yeah, I also don't know. My understanding has not extended to that regime yet.
I see. I
Okay,
see.
any other questions? Okay, if not, I will represent everyone to thank you, Pengfei, again for the very interesting talk and for the very elegant results. Thank you.
Thank you.
Yeah. Bye.
Bye.